Right. Okay. So thank you for inviting me. This is a joint work with Gili Galan, who is now a postdoc at Vanderbilt. And this started a year ago. Von Jones, who is now faculty at Vanderbilt, he turned out that he was working on Thompson group F for about a year. Last year, I mean, now it's 2 years. So I asked him to give a talk at our seminar. The talk was about something quantum, which I still don't know what it is. But he, in particular, he introduced a subgroup of Thompson group F. And since I'm interested in subgroups of Thompson group, we had a paper with Victor Guba about it long ago. So it was interesting for me. And he asked some questions about this subgroup. In fact, he was not really interested in the subgroup, but he was interested in representation over by this left representation on the cosets. And moreover, you take this representation, permutation representation, you linearize it, and you get a presentation by unitary operators on Hilbert space. And that's the representation he was interested in. And one of the questions, I mean, he asked several questions. One of them was, what is this subgroup F? I mean, this Jones subgroup. And whether this representation, linear representation, is reducible. So we answered these questions with Gili in our first paper. And then we realized that we can use this subgroup to answer some other questions, like of Savchuk, about maximal subgroups of F. There existed some questions, and it turned out that it answered this. So we wrote another paper about that. Anyway, so let me start with just general think about F. So what is F? There are many ways to represent elements of F. So the most popular probably is by functions. So it's a functions homeomorphisms of unit interval with slopes. I mean, the piecewise linear homeomorphisms with slopes are powers of 2. Breakpoints of derivative are at dyadic rationals. Okay, so this is what was originally what Von Jones was interested, because he was actually interested in this group, diffeomorphisms of 0, 1. So for this quantum field theory he wanted to construct it, he needed representation of that group. And Thompson group is kind of dense subgroup there. It is well known, and so he's first considered the representation of the Thompson group. Anyway, so this is the first representation. There are several, and for us, the most interesting, I mean, most important for this talk is representation by diagrams, which we did with Victor Guba 20 years ago. And this group is generated by 2 pictures. Let me draw these pictures. So this is called X0, and another one is called X1. So these are diagrams. You can, if you wish, you can, this is a kind of one-component diagrams if you wish. So it's a semi-group diagram. So every edge is oriented from left to right. And you can say that it's labeled by X if you wish. But anyhow, so these are semi-group diagrams, and you can multiply them by just identifying the bottom of one of them with the top of the other one. You concatenate 2 diagrams, you get another one, another diagram, and then, you know, to make a group, you have to do the following. So if you see 2 cells like this, you remove these 2 cells. I mean, these are called cells. These are called cells, the two-dimensional complexes. But anyway, so if you see this, you can just replace it by one edge. And if you see this thing, the opposite kind of picture, it's called a dipole. If you see this thing, then you replace it by two edges. This is called removing dipoles. This is very similar to what you do when you multiply words in free groups, right? So multiply two words in constellation. These are constellations. And you get a group. You get a group. This group is isomorphic to F. If you, I mean, what is nice about this, so every element of the group is a diagram. It has like one edge on top, one edge on the bottom. There is a maximal kind of positive path in this diagram, which separates it into a positive path, positive part, and a negative part. And every edge, sorry, every vertex of the diagram is on that path. Something like this. This is a diagram. Right? Multiply a diagram, you just identify the bottom edge of the one diagram with the top edge of the second diagram. You get a bigger diagram. Concatenate. So identify this edge with that edge if you want to multiply x1 by x0. You identify with this edge, and then cancel dipoles.
Can you draw it?
x0, x1? I will draw it eventually. Huh?
Yeah, x1, x0.
I will draw it later. Okay? I will draw many other diagrams today, so I will draw many pictures. Anyway, so this is a diagram. And so all vertices are on this maximal path. You can also view elements of Thompson group as pairs of binary trees, as more common thing. You just put a vertex in the middle of every edge, and you connect these vertices inside the cells. What you get is a binary tree. And the same thing from the bottom, so you have two pairs of binary. And you can, of course, get, if you start with a pair of binary trees, you get the diagram by just taking the dual thing. Okay, so this is the definition of Thompson group in terms of the diagrams or trees. There is another one, another definition, which is in computational sense, it's more useful. Namely, the Thompson group acts on the set of binary fractions, right? So it's like a piecewise linear function with the breakpoints, dyadic fractions, and the powers of two slopes. Anyway, so how to find the function? How does it act on binary fractions, right? So it acts by substitutions. So every element of Thompson group can be represented something like this. UI goes to VI, 1, and so on. I mean, sorry, UI 2, and so for some I. For I, we'll say from 1 to k, where UI is a word in 0 and 1. VI, I mean, both of them are words in 0 and 1. And the substitution means that if a binary fraction starts with UI, you replace it by, I mean, let's use UI and VI. If you start with UI, you replace it by VI, right? If it starts with UI, you can replace it. So you only can replace the prefix. And the condition is that every infinite binary fraction must start with one of the UIs. Otherwise, it's partial transformation. You want full And another condition is that the inverse, when you replace, I mean, we switch UI and VI, must also satisfy this condition. So every such substitution, every such sequence of substitutions is an element of Thompson group, and Thompson group consists of such. So that's what it is. It's another thing. Now, how to get from here, from the diagram, to substitutions? You do the following thing. So how many of these things? So how many? What's a k? The k is exactly the number of edges in the maximal path. So now, for example, you take this edge. How do you get this edge? Okay, so you first go here, then go here, then go here, and go here. So if you go left, so this is going left. I mean, it looks like going down, but it's left. It's the left edge, and this is right edge of the cell. So you go left. After, each time you go left, you put 0. Each time you go right, you put 1. So here, for this element, for this edge, it is 0, 0, 1, 0. Right? And now, look how the same edge also exists on the bottom. So how to get here? It is, in this case, it is what? Left, 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 left. Right? So it is like, or something like that. Right? So this is substitution. And you do it for every edge on the horizontal path. Right? You get a sequence of substitutions. This is exactly the element of Thompson group, and this is how it acts on binary fraction. So if you have a binary fraction, it starts with this combination of zeros and ones. You replace it by that. Right? So that's how it acts. Okay. Yeah. These trees must move together. Yes. Sorry? Whatever. I mean, this is a classic thing. So I mean, that doesn't matter. So this is how you. There are several other representations of Thompson, elements of Thompson. Computationally, this is slightly better than diagrams. Okay. So now another thing which you need to know about the Thompson group is that. Okay. So first of all, it's 2 generated. Right? You see, the 2 generators, and it has 2 defining relations. Its derived subgroup is simple, right? It's not difficult to prove. It was a classic result again. It is, I mean, it's 2 defining relations, but it is slightly better to consider infinite generating set. Namely, if you define xi to be, where I is at least 2, it is x0 inverse xi minus 1 x0. Right? So just by definition, so if you define, or if you wish, it is something like I minus 1, and it's conjugation. So you just take all the conjugates of x1 by x0. Okay, so this is a infinite generating set of f. And the presentation is, so it is generated by all xi's, and xj inverse xi xj is equal to xi plus 1 whenever j is less than I. Okay, so that's a presentation. Okay, so that's what you need to know. Yeah, by the way, there is another thing which you need to know, which I'm going to use, is that there are several normal forms of elements of Thompson group. There are several of them. If you look at my book about combinatorial algebra, there are 3 there, 3 normal forms there, but there are more than 3. So in particular, it is easier to write normal form in the infinite generating set. And the normal form looks like this. So it is a product. So it is a, so every element can be represented as UV inverse, where U is a product of xi's, V is a product of xi's, positive products, without inverses here and inverses here. And the indices increase, something like x0, x1, x3, x5, x6, sorry, what is it? Yeah, x5, x6, x7, something like inverse, right? Now, again, it is very easy to read off the normal form from the diagram. What you do is you look at each cell, and if a cell, each of these cells, so for example, 1, 2, 3, 4, I mean, first you look at the positive part, right? So positive part of the diagram corresponds to the positive word, and the negative corresponds to the negative, of course. So, so you look at the cells. Now, if the cell touches the right end of the diagram, this point, you just put 1 in it. Otherwise, you put here x with the index, which is the distance from the left point of the cell to the left point of the diagram. For example, this is x0. This is x0. This is x0. This is x1, right? Because the distance from this point to this point is 1, right? And so on. So this is easy to see. OK? Right? For example, here, you see, so you put 1 here, right? Because it touches the right end. You put x0 here. You put 1 here and 1 here. So this is x0, right? You put, the same thing here. So this is 1, 1, 1, x1, 1, 1, 1. This is x1, right? And now you can, everybody, if you want x0, x1, you can just draw it, OK? So I don't need to do it. I will draw some other diagrams. OK? So this is introduction of Thompson into Thompson group. OK, so now what is, why is it was interested, why von Jones was interested, he proved that you can use Thompson group to enumerate all links in the same way you use braid groups to enumerate all links. OK? And so namely, given an element of Thompson group, you produce a link. And given a link, you produce an element of Thompson group. OK, so there is a kind of it's not even one-to-one correspondence, but it's like with braids. Also, with every knot corresponds to many braids, and every braid corresponds to only one knot. OK, so let me draw some picture again. For example, let's take, there are examples in John's paper, which is in the archive. So he used, he constructed representations by element of Thompson group of Baromean rings. But let's do something simple, because I'm not a knot theorist, so I cannot just draw some complicated knot. So this is a knot, right? Keychain. The keychain. I don't know. I have key, but it doesn't matter. This is a keychain, right? It's a link. Sorry, not. It's a link. Link, right? OK. So what element of Thompson group corresponds to this? So what you do, first of all, this is a link diagram. You can paint the regions. So how many regions? 1, 2, 3, 4. 4 regions. You can paint them in white and black, so that 2 neighbor regions have different colors. So it's a white, black, white, black, right? Then you take vertices inside the black regions, and edges correspond to crossings. Now, crossing, there are 2 types of crossings, right? So the positive crossing and the negative crossing, right? It depends on how you trace. So this is, for example, positive, and the other one is negative. So in this case, both of these crossings are positive, so you just put something like that. It looks like a diagram already, but not exactly. OK, so this is the first step. You do this. In this case, it's kind of easy. So we skip the second step, because in this case, you don't need it. But there are some, in general, there are some complications. But anyway, so we have this thing. OK, so now what do we want to do? We want to produce, first we want to produce a part of the diagram. Namely, we take this diagram, for example, we take a diagram, and we remove all right edges. OK, so we have every cell. It has top edge, bottom left, bottom right. So you remove the top edge of every cell, if it is not left edge of some other cell, and remove the right edge. OK? What you get is what Jones called the Thompson graph of an element of Thompson group. Thompson graph. Okay, so actually it's easy to see that only left edges they determine the diagram. Okay, now what do you get? Since you only leave the left edges, it's easy to see that after you remove all the right edges and top edges, remove everything else, leave only left edges, what you get is that in the positive part, you get a tree. Namely, for every point for every vertex, you only leave one edge coming into this vertex. Only one, because all other edges will be right edges of some other cells. Okay? So for every vertex, there is only one edge coming in the Thompson graph. Okay? And so it is connected graph, so it is a tree. And the same thing in the bottom. So what we get is a pair of trees, but a different pair of trees. Right? This pair of trees actually shares all the vertices. So the top tree and the bottom tree, they share all the vertices, and they're just kind of horizontal. He called them bifurcation trees, whatever it is, anyway. So far, so we want to produce a Thompson graph of some element. So far, this is not a Thompson graph. Why? Because this vertex has two top edges coming into it, right? So we have to do something. Now, remember that the link diagrams are only determined up to moves. I mean, there are certain moves that change the diagram but preserves the knot. That's called Rademeister moves. And if you look at what moves correspond to Rademeister moves with, in here, they correspond to certain moves which Jones identified. In particular, what you can do if you have such a situation, we take this vertex, which has two incoming edges. So we divide it into three vertices, and so we put this edge again, we put this edge again, and we put two more edges like this, positive, negative. Okay, so now it is almost a Thompson graph again, except this vertex is not good enough because it doesn't have bottom edge coming into it. You see, it must have bottom edge. So what you do is this, right? And then you do this thing. And the same thing here. Okay? It's again Rademeister moves. So now we get the Thompson graph. Okay? And then you just kind of complete the graph to the diagram. And so on. So compute, which I don't want to draw. And what you get is some element of Thompson group, namely x0 cube, x3 inverse. x3, sorry. x3, because there are no negative x. Okay, so this, I'm sorry, again, it's x3 squared. Okay, so this is an element corresponding to that link. Okay. Anyway, so what is the Thompson subgroup? What's the, not Thompson subgroup, the Jones subgroup of Thompson group? So he described it in the following way. Okay, so now we have this picture, and what you can do from this diagram, you can draw a surface. You can construct a surface whose boundary is your link. How to do it is again standard thing. You put a small disk inside black regions, and then you connect so for every crossing, you connect these two disks by half twist. Half twist, okay? So it's a positive half twist or negative half twist, depending on the crossing. Okay, the boundary of, you get a surface with boundary. The boundary is exactly the link you start with. Okay, so now suppose that you want to get a ciphered surface. So it means that you want the surface to be oriented. Okay, then what does it mean? You see, it means that if you go from some disk along this half twists and return back, you should have the same orientation. So it means that the number of half twists is even. Okay, so that means that the Thompson graph that you started with, which corresponds to the link diagram, must be bipartite. Every loop must have even number of edges, right? So that's a definition of F of Jones subgroup. So T of G is the Thompson graph, which I recall again. It consists. It's a diagram where we leave only the left edges of every cell, the left edge of every cell. Okay, the Thompson graph is bipartite. Okay, so the interesting thing is that this is a subgroup, like a product of two such elements is another element of this. Okay, so the way Jones proved it is kind of complicated, but if you use diagrams, it is really easy to see. Because when you concatenate two diagrams, the bipartiteness actually is preserved, and then when we reduce the dipoles, it's still okay. Okay, so this is subgroup. Okay, so the question is what it is. I mean, the question was when Jones asked what it is. And another question is, okay, so we want to show, you want to find out if this representation, the linearization of this representation is irreducible. Now, this is equivalent to asking whether this subgroup is coincides with this commensurator. I mean, it's hard to believe, but there is a book where it is written, in fact, with the proof. So permutation representation is, I mean, linearization of permutation representation is reducible if and only if the subgroup coincides with commensurator. So that's what we want to show. That. And we proved that with Gilly-Galland that indeed it coincides with commensurator. But this is, of course, not a very big deal. But the other thing was actually very strange, because we turned out that this subgroup is not new. I mean, we constructed this subgroup with Victor Guba 20 years ago. So first of all, so we proved the following thing. So let's call it the theorem number 1. So there are several points in this theorem. So the first thing is that this subgroup is 3-generated. Namely, it is generated by x0, x1, x1, x2, x2, x3. Okay? Now, the fact that each of these elements is in this subgroup is kind of easy. You just draw the diagram, draw the Thompson graph, and look at bipartite or not, right? But the fact that there is nothing else in this subgroup is kind of difficult to understand. In fact, till the very end of writing the paper, I thought that the subgroup is infinitely generated. And why would it be finitely generated? It's completely impossible to just predict. The second thing is that, in fact, this subgroup is isomorphic to what is called F3. Namely, so what is F3? It's a set of it's a group of all homeomorphisms of unit interval with 3 adic breakpoints and powers of 3 as slopes. So why 3? Of course, it's 2 plus 1, but I mean, of course, it's also 2 times 1.5. But anyway, so it's F3 for some reason. The third thing, which actually was mentioned in John's paper without proof. And when I knocked on his door and asked, what's the proof? He said that it follows from his paper. So the statement is this. Consider the set of all binary fractions, all finite binary fractions with odd sum of digits, or even sum of digits. Then this is precisely the stabilizer of this thing. Yeah, so stabilizer of all, yeah, so and so Gilly actually found the explanation of this strange thing is that if you take a Thompson graph and you look at the at some edge here in the Thompson graph, or some vertex, better to say vertex, not the edge. Some vertex, it's a tree, right? So the Thompson graph, it's a top tree and the bottom tree. So there is unique path from the origin to that vertex. Now, the length of this path is the sum of digits in, I told you this, in UI. The sum of digits in UI is the length of this path on the tree. The sum of digits in VI is the length of the path in here. So if you want to preserve the, this set, right? So it means that the sum of digits here and the sum of digits here, the length of this part and this part must have the same parity, right? So it must be, right? And so the graph is bipartite because every loop proved that G. This is clearly a subgroup of infinite index, right? Okay, and of course I told it must be infinite intervals, so there must be lots of. So what we proved, in fact, that there is nothing between them. So it is maximal. So this is a maximal subgroup in G, and moreover, there exist exactly two subgroups of F containing John's subgroup. I mean, three subgroups, namely John's subgroup itself, G, and F. There is nothing else. So it has kind of what I call quasi-finite index. It's a kind of index, whatever, 3, if you wish. Okay? Now, okay, so what you can do, I mean, this is non-trivial fact. This is non-trivial fact, so how to prove that every subgroup which contains John's subgroup coincides with G, or contains also G. This is non-trivial fact, I mean, but it's very, very technically complicated, I would say. Okay? Now, okay. Now, at that time, I also found a paper by Savchuk, Dima Savchuk, and discovered there a question. So Dima Savchuk, he considered maximal subgroups of F. Namely, he proved the following fact. So if you take, let's say, any number alpha from 0 to 1, on the unit interval, and you take all the elements of F that fix alpha, F sub alpha, if you wish. It's a maximal subgroup of F. It's not difficult to prove. It's, in fact, it's exercise, if you will. Maximal subgroup. Of course, there are other maximal subgroups, namely the finite index ones, like G is a maximal subgroup. And he asked if there are any others, because that's a question. And the answer is yes, there are others. And namely, you can do the following thing. OK, so G, which is index 2 subgroup of F, actually is isomorphic to F. There is a nice thing. It's isomorphic to F. So there is an endomorphism, injective endomorphism phi from F to G. If you take the pre-image of John's subgroup, you get a maximal subgroup of F. And this maximal subgroup of F doesn't fix any point, and it's of infinite index, and is not inside any finite index subgroup. Okay, so this is answers the question of Savchuk. Okay, but it's kind of a non-trivial answer. So we wanted to find some other, maybe more natural answer. There must be many such subgroups of F which don't fix any point. So how do you do that? What would you do? Okay, so basically you do the following thing. So you take F, and you take some random elements. So 2 elements. And suppose that you take a subgroup, G and H, and let's call it H. Let's call this subgroup H. And suppose that there are 2 properties which hold. Suppose that H times the derived subgroup is equal to F. So it means that the abelianization of F coincides with the abelianization of H. Right? So the image of H in the abelianization is the whole abelianization of F. And the second thing that H does not fix a point in 0, 1. For example, maybe G is equal to x0. That's a function which doesn't have fixed points, right? Okay. So what else do we want? We want H to be a proper subgroup. Okay, so if this is true, then you take any maximal subgroup containing H, it will be answer to Savchuk's question. Take any maximal subgroup containing H. And since F is finitely generated, every proper subgroup is contained in a maximal subgroup. Take a maximal subgroup M, which is bigger than H and smaller than F, then it will be of infinite index because of this property. Remember that every subgroup of finite index of F contains the derived subgroup. Okay, so if this is true, then the H cannot be contained in any finite index subgroup. And M also cannot be contained in any finite index subgroup. And since H doesn't fix any points, then M doesn't fix any point. So that would be OK. So, OK. So the main difficulty here is how to prove this. So, OK. So you have a subgroup of F, 2 elements of F. How do you prove that this subgroup is not the whole F? What do you do? There are 2 ways to do it. First, you check if this subgroup fixes a point. If it does, then it cannot be the whole F, because F acts transitively on the binary fractions. Okay? And second, you try to understand if H is inside a finite index subgroup. If it does, then it cannot be the whole F, right? But unfortunately, these 2 properties actually tell us that we cannot use both of these things. And there was no alternative. You cannot do anything. And for you, if you kind of get tired, I have a couple of questions. By the way, if you are interested in the amenability of Thompson group, you should, if you don't solve these questions, you just have to drop the subject, because you cannot prove non-amenability. OK, so the first thing is this. X2 inverse and X1, X2, X3 inverse. Is it equal to F or not? OK? OK, the second question is X0, X2, X0, X3, X6. Is it equal to F or not? And the third question, which is actually interested, is this one, X0 and X1, X2, X1 minus 3. Is it equal to F? Equal. Equal. OK? Just equality. So namely, if you wish, is it true that X0 belongs to this subgroup? Is it true that X0 belongs to this subgroup? And X0, of course, belongs to this. So is it true that X1 belongs to that subgroup? OK? I will answer these questions. So, but meanwhile, you can try to answer it. OK? So what is so how to do that? So how to, we cannot use this, we cannot use that. So how to prove that the subgroup is not equal to F? Now, remember, you can actually do this, the generation problem, in 3 groups, right? So if you have 2 words, U and V, and you want to find out if it's equal to, inside Fn, is it equal to Fn? So what do? You do the Stallings foldings, right? So you take a circle labeled by U, circle labeled by V. Consider this as an automaton with this input and output. Okay, and then do the folding. If you see 2 edges with the same label coming from the same vertex, you fold them, right? What you get as a result is this called the core of the subgroup. You get the core, OK? And the subgroup H is equal to F if the core is equal to, like, this bouquet of circles, right? If and only if. OK? So can we do it here for Thompson group? Of course, Thompson group is not free. Moreover, it doesn't have free subgroups. Nevertheless, we can actually do something like that. And let me try to, there is it's almost a diagram here. So what I'm going to use, I will erase, don't worry. OK. So what do you do? OK, so you take two diagrams. For example, diagram corresponding to this element, a diagram corresponding to that element. OK? And what you do, you identify, you make a sphere. You make two spheres. You identify the top edge of one diagram with the bottom edge of that diagram, and with the top edge of the other diagram, with the bottom edge of the other diagram. So you have, OK, so for example, OK. Again, so let's do this x0, x1. This is x0. So I like drawing x0, x1. So I once asked my daughter to draw a trefoil knot. And she actually turned out that she can do trefoil in like about 15 seconds. John said that he could do trefoil in 5 seconds when he was younger. So you have to, if you're a geometric topologist, you have to do it like in under 10 seconds. But anyway, so I cannot draw trefoil, but I can draw diagrams. So this is x0, this is x1, generators of f. OK? So you identify the top edge and the bottom edge, the top edge and the bottom edge, and you identify all the 4 edges together. And then every time you see a cell, 2 cells, right? So it's one cell and another cell with the same top edge, something like that. You identify the cells. So if they have common top cell, top edge, you identify the other two edges, right? So you identify 2 cells. It's a folding, right? What you get is what I call the 2 automaton. Now, every reduced diagram, reduced means there's no dipoles, in the subgroup generated by 2 diagrams is accepted by these 2 automaton. Namely, you can actually read the diagram starting from here and ending the same ending back in this edge. Okay, so let us see what kind of automaton you get when you start from x0, x1. So this automaton actually is kind of analog of the bouquet of circles. Okay, so let's do that. So this is edge 1. This is edge 1, 1, 1. Right? Okay. So you have cell here and cell here. They have the same. But anyways, we have cell here, so you have to draw. You have to make this edge 2. This is edge 3. This also cell has top edge 1, so it must be 2, 3 here, and this is 2 and 3, right? Because it's edge 1. The left edge is 2. The right edge is 3. Okay, so now we have this one cell which is 2, 4. New edge 4, and that's complete, right? So here, everything complete. 3 is 4, 3. Okay, so we have, we have how many edges? 1, 2, 3, 4, 4. And now we do the same thing here. So we know that this is 1, this is 2, this is 3. 1, 2, 3. 3. You see, if you see 3, then the left edge is 4, the right edge is 3. So this is 4, 3, yes. Okay, so now this is 3, so it must be 4 and 3. And this is 4 and 3, so we have this thing. Right, so that's it. This is automaton. Right, so you have to identify, now we have this automaton, now we have to identify edges which have the same labels. Right, so we identify these 4 edges, we have to identify all 2s, all 3s, and all 4s. Okay, so we have a 2 automaton with 4 cells. So the bouquet of circles here is a 2 automaton with 4 cells. Okay, and it accepts, of course, every reduced diagram of F. Okay, good. So now, okay, so now let's do a similar thing with. First of all, okay, let's consider this subgroup. Okay, and draw a 2 automaton for this subgroup. Okay, so let's do that. So x0 is already here. Okay, so I will draw x1 again, but okay, doesn't matter. So let's draw a diagram for x1, x2, x1 to the power minus 3. So this is x1, this is x2, right? And then we have to do x1 minus 3. So it is x1, x1, x1. Right? Did you follow the fingers? This is, you see, it's much easier to do than trefoil. So this is x1, x2, x1 to the power minus 3. Okay? Right? Okay, so now let's do the automaton. Okay, so this is 1, this is 1, this is 2, this is 3. 3 is 4, 3, so this is 4. Sorry, this is, must be also like this. 4, 3. And then what? 3 is 4, 3. This is 3, 4. Sorry. Huh? Something is wrong here. Yeah, it must be like here, right? Or something like this. No, just a moment. Yeah, this is true, but then also there is this is true. Okay, so otherwise it's, okay, so it's, again, this is 4, this is 3. This is 3, this is 4, 3, and then 4. Okay, so let's call this 4 is 5 and 4. 5 is 6, and let's see, this is 4, 5, 4, 5, 4, and 5 is 6 and 4. Okay, that's what it is. All right, let me see. I probably made a mistake.
Easier than drawing a checkpoint.
Yeah, it's easier than, I mean, to draw it's easy, but then you have to put these numbers in, and I think it's correct. Yeah, it is correct. Okay? Okay, so now let's try to read x1 and draw x1 again, the third time. Okay, so this is 1, 1, 2, 3, 3, 4, 3, 4, 4, 5, 4, 1, 2, 3, 3, 4. Sorry. Yeah. Here it is already, right? This cannot be read here, because here you would have something, the cell which has 3 on top, 5 at the left edge, and something on the right edge. But we don't have cell like that here, right? 3 is, what is 4 and 3? Since 4 is not equal to 5, right? It's important to know. Then this thing is not read here. So x1, in fact, does not belong to H. And in fact, H is indeed a proper subgroup. So this is, the answer is no. Okay? The answer is no, and that's it. So yeah, by the way, you also need to see, okay, why is it not inside finite index subgroup? It's easy, because if you look at the abelianization, it goes to x0, and this goes to what? x1, x1, x1 minus, so it goes to x1 inverse, right? I mean, in the abelianization, x2 is equal to x1, because it's a conjugate of x1, right? So this is equal to image of x1 inverse, and this is equal to x0, so the image is the whole abelianization of f, so it's not inside finite index subgroup. Now, the other question is, why doesn't it fix the point? It not only doesn't fix a point, it doesn't stabilize any proper subset of rational fractions, of rational binaries. And the way to do it is another theorem of Gilly and myself. It's Gilly, Galan, and myself. So we proved the following things. There is an algorithm given a subgroup, given a finitely generated subgroup of F. There is an algorithm to check whether the subgroup acts transitively on binary fractions or not. And the algorithm is the following. So take the two automaton and consider the new graph associated with that. Namely, the vertices of this graph are edges of the automaton, right? So in this case, what is it? 1, 2, 3, 4, 5, 6. There are 6 vertices, and 2 edges are, hi is related to h, is adjacent to hj, if j is the left edge of the cell with top hi. For example, with top hi. For example, 3 is related to 4, right? 3 is related to 4. Okay, so consider this graph of the subgroup H. Now the statement is the group H acts transitively on a set of binary fractions if and only if this graph has a unique cycle. Plus every vertex has a child. Vertex has a child, so every vertex has something to the left of it. So there is for every edge of the 2 automaton, there is a cell which is where this edge is top edge. Except there is one exception, except for the edges which are initial edges, which come from. So every edge which is not initial edge has a child, and the graph has unique cycle. Okay? For example, here. Okay, so we only need to consider edges 3, 4, 5, and 6. So what do we have? We have 3 goes to 4, 4 goes to 5, 5 goes to 6, and 6 goes to 5. Unique cycle. So the group acts transitively on the set of binary fractions. Okay? Not only doesn't fix a point, but acts transitively on a set of binary fractions. Okay? So the graph of H has a unique cycle of edges, not initial edges, non-initial, initial edges, if and only if H acts transitively on the set of binary fractions. It looks, sounds kind of crazy, but it's true fact. Okay, yeah, I need to finish now. And so the last thing I want to say is, okay, so there is an open problem, the generation problem. So now, given 2 elements, you want to find out if they generate F. Conjecture is they generate F if and only if this subgroup is not inside finite index subgroup, which is algorithmically verifiable. And the second thing is that the 2 automaton is this 4-cell 2 automaton, so bouquet of circles. Okay? We cannot prove this conjecture. And the very last thing is that the answer is yes in here and in here. So this is F and this is F. Here, like x1 is a product of these things of length 96. And here x1 is a product of these 2 things of length 47. So, okay, that's it. Thank you.
Well, a couple of quick questions.
He considered, yes, these are subgroups coamenable. Yes, that's true. The Thompson group, we don't know. So what we know, so the subgroup is called coamenable if the Schreier graph is amenable. So what he proved is that his subgroups, this is called F alpha, I call them, they're coamenable. But they're coamenable for some easy reason. That's because the Schreier graph contains like embedded infinite lines. So what we prove here is that the Schreier graph of the Jones subgroup does not contain infinite lines. So we don't know if it is amenable or not. It may be equivalent to amenability question of F.
So do you know if any of these subgroups is distorted enough?
None of them is distorted, no. None of them is distorted.
None of them is distorted?
No.
Let's thank, well, let's thank Mark again.